Hello. Probably doesn't seem so to you, but to me it has been a long time since I have been able to record something for you. I don't even remember the last one. It was before you handed in the exam. So it's been a while. Let's just say that. Don't forget, you have your second quizam on Friday. Friday or Saturday as you wish. You have half an hour for it, including processing time. I recommend 25 minutes for it and 5 minutes of processing time. That's our next step. I have returned, and you've read other people's comments on the problem set. That's what you were doing on Monday, I hope. And now, a bit later, sorry about that, but it was the way things turned out in the schedule. I will wrap up question 3 from the exam. Then we will start into section 10.2, where we are looking at more of the fundamental theorem of calculus. So obviously, in particular, more work with line integrals, which will seem familiar because you saw something about them on the exam. You did something on them on the last problem set. So despite the fact that I'm lecturing about chapter 10 and you just finished work in chapter 4, they're very tight. It's not a world away. Speaking of a world away, question 3 on the exam was our only interplanetary question. And so away we go. Let me just talk through this. I won't include all the details, but I do want to include some of the highlights. I thought it was a fun question. As I hope you noticed, some of it came out of some of my comments in lecture as I realized some interesting things about escape speed on Earth and what it meant. So we were given the mass of the sun, the mass of the Earth, the mean distance, or if you prefer, semi-major axis of the Earth from the sun. It was given in kilometers. You probably wanted to quickly change that into meters. That's probably would have been a good idea. You were also given the eccentricity of Earth's orbit. Earth's orbit, by the way, is pretty close to a circle. That's pretty close to 0 as far as things go, but it's not exactly 0. So our orbit is an ellipse. It's just a highly circular ellipse. Some things we know from the book. The semi-major axis, which is the same as the mean distance that the Earth is from the sun, is given by this equation. So from this equation, we know, why am I eccentricitying with an E and not an epsilon? I don't know. We know the eccentricity. We know the mean distance from the sun. So from that, we can find out what gamma is. And I've already shifted into meters. Physicists out there are going to complain and say I'm being careless with significant figures. And yeah, you're right. And I shouldn't be. So I'm not claiming those digits are all significant. I surely wasn't expecting anyone to be careful with significant figures, but the flip side is anyone who was, I wasn't. I was completely respectful of that. All right, from this, we have in the book equations for apogee and perigee. And we know gamma and we know epsilon, so we can find both of these. And again, these are the significant figures are not right. Here, this one might be. All right, notice, so like I said, the Earth's orbit is highly circular, but not quite. These aren't the same, but they're pretty awfully close. All right, so we know those things, that's great. We might like to find K. Gamma is K squared over GM. This is M of the sun. We know gamma, GM of the sun. And so from this, we can find K. K is 4.4557 times 10 to the 15th. I don't happen to have units on this at the moment, but I'm mostly okay with that, given that I'm going to use K to get something else pretty soon. All right. So from this, we have a couple of things. So there's K, great. For apogee and perigee, the velocity times the distance from the sun is equal to K. That's because there the angle is pi/2 between the velocity and the distance, or the radius, the radial direction. So they just multiply. We don't need to use any fancy cross products there for our vectors. And so at apogee and perigee, we can use this to find the velocity. Just find K divided by the distance, and there's the two distance. There's K, so how hard can that be? We get 2.294 and 3.029, and these are both in meters per second. Okay, great. We can also find the escape speed. The escape speed, this is the speed for the Earth to escape from the sun. So what it takes to get out of the solar system. This is now pointing us toward the question that Bressud implied, and I tried to follow him, and then I got tempted into believing him, I think. So the escape velocity is given by 2 GM of the sun divided by the distance. And I like this. Some people said, well, all right, we have 3 different distances we could use here. We have lots of others, but we could use the mean distance, the apogee distance, the perigee distance. They all give slightly different escape speeds. And that's worth noting. So if you want the escape speed to be large, I guess, I mean, you don't. If you want to get off the Earth, you do it when you're furthest from this. You know, if you want to get off, yes. All right. If you want to get away from the sun, you do it when the Earth is furthest from the sun at apogee. So that makes this the lowest possible. I computed this for mean distance because I wasn't being as careful as you guys were. But I do respect completely that many of you were being careful, and I appreciate that a lot. And so what we look at then, and this is, which one's which? This is also, so the velocity is lower. So this is at apogee, and this is at perigee. And so you pick 2 of these, and then there's also, oh, by the way, the escape velocity from the Earth. This is the escape velocity from the sun at the Earth. The escape velocity from the Earth is from the book, and that's 1.12 meters per second. That's from the surface of the Earth. That's, of course, absolutely wrong. It's right, but obviously needs a 10 to the 4th. Otherwise, this is pointless. All right. So we have these bits of information. And the question is, if you escape from the Earth, do you also escape from the sun? And the first answer looks like, well, that's not even close. Those numbers aren't the same. But the second answer is, wait a minute, because you do get to use the Earth's speed, because if you start on the Earth, you're moving with the Earth, so that's part of your velocity. So if you go in the same direction that the Earth is going, then you get to use one of these numbers, let's say this one. And then you ask, if you add these two together, do you get that? And the answer is still not quite. It's close. It's really close. It was close enough when I recorded the last lecture on this topic. I was going to say, yeah, probably. But the answer is not quite. The interesting thing is, to get into that little bit, you'd have to be pretty careful on your velocity. So if you wanted to escape the Earth and not the sun, the precise speed you would need is between the range of the sum of these two and that, which is not a whole lot of difference. So it's close. For the Earth, if you launch a rocket on the surface of the Earth, it will get, so that to escape the Earth, you're close to getting the velocity you need to escape the sun and leave the solar system and go to the ends of the universe, as Brasoud said. But not quite. And okay, so it's close, but not quite. And that's, I think, what you take away from the Earth. And now I asked you to do one thing more, and that was to think about other planets and how it would compare there. Just using your common knowledge of other planets. Remember, by the way, the mass is proportional to the radius cubed here. So the radius of a planet is not really very important as much as the mass of the planet is important. The mass of the planet determines the escape velocity. The radius of the planet, yeah, it has some effect, but not so much. So I want to think about two planets to begin with here. I'm going to sit down because I'm not going to write so much about this. For Mercury, Mercury is very small, but also very close to the sun. So the escape speed to escape from Mercury, because it's very small, will be much lower than the escape speed from the Earth. But because it's much closer to the sun, the escape speed from the sun, where Mercury is much higher. So given this reasoning and the fact that Earth is almost identical, I think we can pretty clearly see if you hit Mercury's escape speed, that's nowhere near guaranteeing you're going to hit the escape speed for the sun. Let's take the opposite point of view. Let's think about Jupiter. Jupiter is much further out than the Earth is, and wildly much bigger. So to escape from Jupiter, the escape speed at Jupiter is much larger than it is on the Earth. And the escape speed from the sun at that distance is much smaller. Because they're almost the same, they almost add up to be the same on the Earth. On Jupiter, it's pretty clear that if you hit escape speed on Jupiter, you've surely escaped the sun. The same thing is also clear for Saturn, Uranus, and Neptune. That's pretty clear. They're bigger than the Earth, far bigger than the Earth, and they're also way further out there. So those three all settled. This leaves Venus and Mars, and Venus is smaller than the Earth, not by much, but it is smaller than the Earth. So its escape speed would be a little bit lower. It's also closer to the sun. So the same reasoning that we used with Mercury should apply on Venus. Escaping Venus's gravity is not enough to escape the sun's gravity. Mars, I don't think we can heuristically decide. Mars is going in opposite directions. Mars is significantly smaller than the Earth, and it's obviously further out there. So because it's smaller, this number's lower. Because it's further out there, this number's lower. And now I don't know anymore. I've lost track. I'd have to go and do the computation. So that seems, that's interesting. I think it's interesting to think about. This only arose because when we were talking about it, and Brasu made that comment and I was lecturing about it, I thought, hey, it looks like the speed of the Earth plus the escape speed of Earth are about the same as the escape speed from the sun. And that's true. It is about the same. It's a little bit less, but it's about the same. And I wondered, hey, is that always going to be the case? And the answer is no, there's no way that's always the case. Just a little coincidence. And it's not like it's exact. So, I mean, if there were a physical reason that would make it exact, it would think it would have to be exact. But it's not. All right. So that's some things about question 3. Fun little things to think about, I would say. So, all right. Let's take a breath, take a break, erase the board, and we will talk about 10-2. How are we doing on time? Yeah, we're doing okay on time. We're doing okay. I'm glad that I got the computer to keep that time for me. Seems like an obvious thing. I'm stalling while I'm erasing the board. All right. At the end of Calc 3, you talked about line integrals. I am absolutely sure that everyone talked about line integrals at the end of Calc 3. And our work on line integrals here is kind of the last guaranteed connection to Calc 3. But we are thinking about them in a different way than before. So, okay, here we go. So here's the first of our proofs of fundamental theorems. This is the fundamental theorem of line integrals. This is 10-2. All right. And all of our proofs eventually will go back to the Calc 1 fundamental theorem of calculus. And I did actually prove that sometime in recent history while I've been slowly working through chapter 10. So we know that's true, and you also have known it for a long time. All right, the fundamental theorem of line integrals says, suppose C is a differentiable path from A to B. Omega is a one form, and omega is the total derivative of a function. Remember, functions are zero forms, and we do take total derivative here, which is each of the partials times the associated differential there. Then the integral of omega over this curve is equal to the integral of the boundary of f, because omega is the derivative of f. And this gives us the boundary of the curve is just a and b. So this gives us f at b minus f at a. And I guess I should point out f here is a vector valued function. So maybe I'll emphasize that and make it clear. All right. So here we go. The proof here is actually not that bad. So I might even be able to fit it in this little space. So suppose that omega is something that is a function of, who knows how many variables we have here, by the way. This is true in 3 dimensions, it's true in 2 dimensions, it's true in 4 dimensions, it's true in arbitrarily many dimensions. However many dimensions our curve happens to be running around in. So I will do this in general. This x vector is then the points on the curve as we're roaming around in whatever space we have. We could call this, so here's a, there's a dx1 missing here. Here's what amounts to a vector valued function, omega, as you're used to actually in Calc 3, omega is a vector field. So it says for every point in space you have a vector, and these are the components of the vector. We could call omega actually, or at least associate it with some vector field. That is something that you put a vector in and you get a vector out. All right, and our curve is some parametrized curve that is vectors for every time value, and time values go from A to B. I'm hoping you'll be comfortable with this. I'm actually, yeah, I think you'll be comfortable with this. Time A, it goes into x vector of A. So we have x vector of A is the starting point. To be clear here, maybe I'll write this here. A vector is x vector of time A, and B vector is x vector of time B. So that's how those two things relate. I think it's probably good to use the same notation there because they're very related. But remember, without a vector, it's a time. With a vector, it's a location. All right, and we are given that omega is the derivative of some zero form or some function. Another way to say that is that since omega is the derivative of that, this vector field is the gradient of some function. This is wrong. I was wrong there. That's not a vector. That's just a function. It's a scalar function. All right. So we are given that each of these fi's, these functions here, are the partial derivative of f with respect to I. Okay. So now let's start on this side and see if we can end up on the other side. That seems like a decent way to do this. We've done all of the setup work. So now we're computing a line integral of this line integral, and we parameterize our curve, and we get the integral from A to B of things like f1 dx1 dt. These are A's and B's are times, plus all the way up to fn dxn dt. This is all integrated with respect to time. So now we've put in our curve and parameterization into our line integral. But remember, each of these functions, each of these scalar functions is just a partial derivative. So this is from A to B of the partial of f with respect to x1 dx1 still dt. And the same thing for all dimensions. But now notice by the chain rule, this, all of these, this is just the derivative of f with respect to t. All of this is our multidimensional chain rule, which gives us not del anymore. df dt. And now what we have here, so contrary to what I said before, f is actually a value in space. We've thought about temperature, for example. So it's a scalar value at any point in space. But we've now rewritten and thought of f as changing with respect to time as we travel along the curve. And now what we have here, this is just our Calc 1 fundamental theorem of calculus. We have a function that's changing with respect to time. We're integrating the derivative. And so we get the value at the endpoints. We get f of x minus f of x a. Wow, what a mess of vectors and not vectors up there. And x at time b and x at time a is just point b and point a, respectively. So that's our proof. Key detail here as the Calc 1 fundamental theorem of calculus. Pretty nice detail here of the chain rule in arbitrary many dimensions. And then knowing what it meant that omega was the derivative of some other function, that given was to us. So we have this result. This result, it's worth emphasizing, needs this hypothesis. The fact that omega is the derivative of some form is a big deal here. In particular, this result says that this integral, because it only depends on the two endpoints, this says that that integral is independent of path. You know from your exam work that that doesn't always happen. Sometimes line integrals are independent of path. Sometimes they aren't independent of path. What we've seen here is if the one form is a derivative, then the line integral is independent of path. I'll say that again. I'm not going to write it in words, but it's important. If the one form is the derivative of a function, by the way, no, it's not a vector function, silly cursor. If the one form is the derivative of a function, not a bad idea to think if we're thinking in terms of a force field, if the force field is the gradient of a function, not a bad idea to think of it that way. If the one form is a derivative of a function, then the line integrals are independent of path. Force field, if your force field is the gradient of some function, then the work done from one point to another is independent of the path you take to get from one point to another. All right, so let's continue pursuing that idea and see where it takes us. But that's what we have so far. How are we doing on time? Pretty good, pretty good. All right, let's see. I think I'm going to take pretty much all this away. So there's the fundamental theorem of line integrals. Woohoo! We're not going to just move on to the next one, though, because there's lots of interesting things we can figure out about this. So first of all, let's just get some language so that I don't have to keep saying, is the derivative of a function or is the gradient of something? We will say, this is just terminology, if omega is the derivative of some function, we call omega exact. All right, so if a differential form is exact, if a one form is exact, then the line integrals of that one form are independent of path. All right, great. I've said that enough times that I hope it's starting to become familiar. Turns out, and this is relevant for lots of reasons, the derivative of a derivative is always 0. This is helpful. Why do we want to know this result? Because we want to know if something is or isn't exact. And this says if the derivative of a differential form is not 0, then that differential form can't be the derivative of some function. Right? If it were the derivative of a function, then this would be the derivative of that function. That's guaranteed to be 0 according to this result. All right, so let's see about this. And this, by the way, that's why we're going to use it. But this here is omega of any order. No matter what differential form we have, if it's a 1 form, if it's a 0 form like a function, if it's a 4 form that's of order 4. No matter what order it is, the derivative of the derivative is always equal to 0. To prove this result, what do we got? Well, one thing that's worth noticing is the derivative of omega 1 plus omega 2. Well, the derivative of omega 1 plus omega 2 is the derivative of omega 1 plus the derivative of omega 2. And then the derivative of this sum. So we can separate this apart. That's not shocking. Because of that, it's good enough to do this just with one term. It's not necessary. It could be that things cancel, but they don't. We will prove actually, I mean, if it's going to hold for all of them, then it should hold for any one term. So I don't need to check it for more than that because of this. So only one term will suffice. I can check it just for one term, and I don't need to worry about the others. So let's try that out. I think I'm going to get rid of this. We can remember that, and we would just check it for one term. So we will let omega be an arbitrary differential form of who knows what order, apparently k order for me. And x will be some vector of dimension n. And n better be at least as big as k. Otherwise, it doesn't make sense to have so many variables in our form. All right. So away we go. What are we going to do? We're going to take two derivatives. Not shocking. So the first derivative is, well, okay, we have some scalar function here. We will take all of its derivatives, and there are n variables total. If, by the way, k was equal to n, this would be guaranteed to be 0 already. Not this, but the first derivative would be 0 because there's no new variables. But there are new variables, so we have things like del f, del x, del k plus 1, dxk plus 1. Then we're just finding the total derivative of f here, ignoring the first k variables, because the first k variables will cancel with these differentials here when we multiply them out. I think I will save us a little bit of board space again. We have this for all of our variables after k up to n. So this goes up to del f, del xn, dxn. And this still has the dx1 up to dxk. All right. And if we were to write this in summation form, which might be easier to work with soon, we have del xj. J goes from k plus 1 to n. And we have dxj, dx1 up to dxk. All right. So that's the first derivative. Now the second derivative that's probably fine. The second derivative then is a similar thing, but now we take extra derivatives of this. And now I'm going to keep using summation notation. So, all right, we have the j going from k plus 1 to n. We have a new index as we take derivatives of this. So we will say I goes from k plus 1 to n. And now we have the second derivative. So the second derivative of f del x I del x, which one's first? All right, we already did j, so we do I afterwards, which means it comes in the front of it, good. And dxi comes out when we took that derivative, times all the differentials from before, dxj, dx1 up to dxk. How are we doing on time now? Yeah, we're getting along, but I think we're still doing great. All right. So this is the second derivative. But now there's a couple of great things that show us why this is guaranteed to be 0. Really, they're here. That's what we need to pay our attention to, is this second derivative and the dxi, dxj. By the way, the places where I and j are equal, dxi and dxj will be the same thing, and those just drop out entirely. As we know, dxi, dxi is 0. The other thing that happens is two things happen here. One thing is, I hope you remember from Calc 3, that del f dxi, or del f del xi del xj is equal to del f del xj del xi. Mixed partials are equal, which was a nice thing there. It didn't matter what order you did those in. So we have two coefficients here that are equal depending on whether we choose I or j first. And we have the dxi dxj is the negative of dxi dxj. So there are what? This is like we in this have a square array of partial derivative differentials that we're all adding up, right? We're adding up all of these, and there's whatever n minus k of these and n minus k of those. So altogether, there's n minus k whole thing squared of things here. The ones in the diagonal are all 0 because dxi dxj, or dxi dxi is 0. The ones off the diagonal all have one that matches up to it on the other side of the diagonal, matches up in two ways. So if I took, for example, dx5, or del squared f del x5 del x7, somewhere there's del squared x del x7 del x5. The coefficients in the front are the same because mixed partials are equal. But the differentials, we have dx5 dx7 and dx7 dx5. Those are opposite order, so their signs are different. So they cancel out. We had a schematic here of the square. The things in the diagonal are all 0 automatically because I have repeated differentials there. The things off the diagonal have something symmetrically that cancel with them. And so all together, we get 0. No matter what our differential form was to begin with. Okay, so that's nice. All right. This gives us some other new language. I'm going to take this away because now we know that this result is true. So the second derivative of any differential form whatsoever is 0. That's interesting. And let's have some more language. Especially because of this here. We will say omega is closed if d omega is 0. So this tells us something. Just trying to put our terms together. If omega is exact, that is, if omega is the derivative of something, that we set up here, then omega is closed. Then if it's the derivative of something, then its derivative itself is 0. Okay, that's fine. That comes from here. This is more useful in contrapositive. If omega is not closed, then omega is not exact. And that's important because this gives us another way to show that omega is not the derivative of something. We talked earlier about if it's exact, then the integral is independent of path. Well, this is a way to know that omega is not exact. A pretty easy way. So if I want to know and try to find out something about omega, I want to know, is it independent of path? One thing I could do, which is a pretty easy thing to do, is take its derivative, see if we get 0 or not. If we don't get 0, then it's not the derivative of something. So we can't apply the fundamental theorem of line integrals. By the way, we use this, why do we use this word closed? We call it closed because of its relation to boundary. We call a manifold or surface or anything, we call a manifold closed if it has no boundary. So we call a manifold closed if the boundary of that manifold is empty. You should here think of a circle has no boundary. A sphere has no boundary. Maybe a torus has no boundary. You should be thinking of things like that. And it's also interesting related to what we have here. For a surface, we have the boundary of the boundary is always empty, much like the derivative of the derivative is always 0. So if you think, for example, of a hemisphere, its boundary is a circle, and the boundary of that circle is empty. Or if you think of a torus with torus like an inner tube with a bunch of holes in it, the boundary of that is the circles of all the holes, and the boundary of that is again empty. So those are some ideas. Yeah, I'm thinking we should probably wrap up here now. It's worth noticing we have a lot of if-then statements. If a differential form is exact, then the integral is independent of path. If a differential form is exact, then its differential form is closed. What we don't have, and we'll start thinking about next time, is these if-then statements are not if and only if statements. It's not the case that if it's closed, then it's exact. We will find counterexamples to that. And what we'll be doing next time is starting to dig through some of the details of when we do have independence of path and when we don't. Can you have independence of path without it being exact? That's another question we could ask. We have lots of questions to think about. We will come back to those next time as we continue on our work in section 10.2. Don't forget you have a quizam on Friday, Saturday. Thank you, and I am glad to have a chance to talk with you again. I look forward to hearing from you as always. Bye.